Welcome to this video number 12 about second order filters, RLC filters. Here we see the first order filter we have been looking at previous videos. Here we have the second order low pass filter. Notice that when it's a low pass filter, we take out over the capacitor in both cases. The second order low pass filter is made up of a series resonance circuit of a resistor, inductor, capacitor, but we take out over the capacitor in order to get the second order low pass filter. Second order comes from that we have two energy storing elements in the circuit. We have an inductor and a capacitor. In the first order low pass filter, we have only the capacitor as energy storing element, so therefore it's called the first order. Down here we see the Bode plot of the first order filter. It has a slope of minus 20 dB per decade, as expected. But the second order low pass filter, depending on the quality factor of it, it has a kind of a peaking or can also slope down here, but the slope is minus 2 dB per decade. Due to it has two energy storing elements, the slope is actually the double of the first order low pass filter. So it's more selective in reducing unwanted frequency behavior into our signal. So this is the benefit of using a higher order low pass filter compared to a first order low pass filter. We get more attenuation, but of course on the cost of an extra component. The equation we use for the low pass filter of second order is of course the resonance frequency and the transfer function. A thing we have to notice is in order to get a maximum flat curve, why is that important? Well, if we have a small point here going up, we actually have a gain at that frequency, at the resonance frequency. This is not always wanted that one specific frequency is higher than the others. The maximum flat one would have a Q of 0.707, but due to component tolerances, we normally always design with a Q of 1. And then we verify our design by LT-SPICE or a similar simulation circuit. If we need higher order filters than the second order filter that slopes with minus 1 dB per decade, perhaps we need a filter that slopes with minus 100 dB per decade. That would be a fifth order decade filter, because the 100 divided by minus 20, that gives the order, that's actually 5. So we would then turn to filter books, and have a look up on how to design a fifth order filter in case we need really to attenuate one specific frequency. Butterworth function. We will see later that the Butterworth function is one that gives a maximum flat slope in the magnitude in dB of the filter. This is normally wanted so that we don't have this peaking. The only place where peaking is relevant in a filter is when we use it as a resonance circuit in an oscillator. Otherwise, they are not very wanted, and therefore we go for a maximum flat function. Here we have the second order high pass. Notice that similar for the low pass, we take out over the inductor. So the sloping upwards here for a second order high pass is, as you can see here, a step of um, a decade. We actually go up with 40 dB per decade. So where the low pass is sloping downwards with minus 40 dB, the high pass is sloping upwards with 40 dB per decade. And again, depending on the quality factor of this series resonance circuit, we can have a maximum flat one, that's around series resonance of 1, or we can have some peaking when we go up on higher values. So for low pass and high pass, the series resonance quality factor needs to be around 1 when we design the filter. When we look at a second order bandpass filter, then we actually try to get a higher Q than the quality factor than for the low pass and the high pass, and that's due to we want the filter to be selective, and the higher the Q, the quality factor, the more selective the filter is in filtering out the unwanted frequencies. And here we have the equation for the resonance frequency. That's the center point, the bandwidth, so how wide it is, 3 dB down from the center frequency. The bandwidth can be calculated by here, and also we're using the resonance, the quality factor for the series resonance circuit are the same. A second order band rejection filter, also called a notch filter, has the output over the inductor and the capacitor, not the resistor. So this filter is filtering out one or few specific frequencies that are a problem. Typical 50 Hz hum in Europe, 60 Hz hum in the US is very typical to apply this filter to filter out this humming effect of audio signals. Here, a higher Q means that it's more selective in filtering out one specific frequency. The wider the Q, the smaller the Q, the more other frequencies it filters out too, and that perhaps unwanted. We use again the resonance frequency and the series circuit's quality factor to design the filter. Thank you for watching video number 12.